The structure of part of a polyester chain is shown below. So we've got a polyester, the COO here, and we've got a long chain molecule. Which statement correctly explains why plastics made from this polyester only soften at high temperatures? Well, first of all, soften. To melt them, you're breaking the intermolecular bonds between the chains. You're not actually breaking the bonds within the chains. It's the intermolecular bonds between the chains that you're breaking to separate the chains to make it soften. So that's the first thing. Hydrogen bonds and van der Waals, so they're intermolecular bonds, forces exist between polyester chains. So for a hydrogen bond, I need an oxygen bonded to a hydrogen, a nitrogen or a fluorine. And I haven't got an oxygen bonded to a nitrogen, hydrogen or a fluorine. So I haven't got any intermolecular hydrogen bonds. Permanent dipole-dipole forces and van der Waals force exist between polyester chains. Yes, that's true, because I've got a polar bond here with my oxygen more electronegative than my carbon, so this would have a delta minus, this would have a delta plus. So I'd have a polar bond, and then I'd have in an adjacent molecule, I'd have another polar bond, and I'd have dipole-dipole attractions between the polymer chains. I'd also have van der Waals force, of course, the attraction between the electrons in one molecule and the nuclei in another molecule. I'll always have van der Waals forces as intermolecular bonds. So B is correct. Let's just check the other. The carbon-carbon bonds in the chain are strong. You're not breaking the carbon-carbon bonds within the molecule. You're breaking intermolecular bonds. The carbon-oxygen bonds in the chain are strong. No, you're not breaking bonds within the chain. You're breaking bonds within the molecule. Your answer is B. The nitration of benzene used in nitrating mixtures follows: concentrated nitric acid and concentrated sulfuric acid. Which statement is correct? This is quite tricky. HNO3 acts as a base. Well, let's have a look what's lost. From HNO3 has become NO2. So I've lost an H, I've lost an O, and if it's become plus, it's lost a minus. I've lost an OH minus. So it is acting as a base. Bases like sodium hydroxide, potassium hydroxide make OH minuses, which then accept H pluses and make water. So a base produces OH minuses, which accept H pluses. So H3O is acting as a base. Let's just check out the others then. HNO3 is acting as a catalyst. That means it's reformed on the right hand side. No, it's not. HNO3 is acting as an electrophile. An electrophile is something that bonds with a double bond, like a carbon to carbon double bond, like in electrophilic addition with HBr across a double bond, or sulfuric acid across a double bond, or Br2 across a double bond, or reacts with a benzene ring. It's not accepting any electrons from a double bond or a ring from sulfuric acid, so it's not C. HNO3 is acting as a reducing agent. Let's just check that out. Oxygens are -2, so 3 -2s are -6. A hydrogen is usually a +1. So -6 add 1 is -5. So the nitrogen must be +5. +5 + 1 is +6. And 3 -2s is -6. So that nitrogen is in +5. Here I've got two minuses. 2 minus on the oxygen times 2 is -4. And it's -4. There's 1 plus over on the right hand side. That's +5 as well. So +5 there, -4 to leave 1 plus. So it's not been oxidized or reduced at all. So it's not an oxidizing agent or reducing agent. The answer is A. Aqueous solutions of ammonia, ethylamine and phenylamine are prepared. What's the correct order for the pH values of these solutions? Well, let's have a look at something like phenylamine. So you're looking at the availability of the lone pair on the nitrogen. You could say, you wouldn't say this in an exam, but you could say, is it large or is it small? Is it a large electron pair, lone pair, or is it smaller? The larger the electron pair, or we say the more available the electron pair, that's the correct way of saying it. So the more available, or the larger the electron pair, the more likely it is to accept an H+, react with an H+, and act as a nucleophile by donating the pair of electrons and react with an H+. That's what a base does, react with an H+. So this one, a phenylamine, has got a low availability of a lone pair because the electrons here are being withdrawn into the ring. Nitrogen hasn't got any withdrawing groups or any electron repelling groups, whereas something like a CH3 or a CH2 would repel electrons, increasing the size, or as we say, increasing the availability of the lone pair of electrons to act as a nucleophile, as an electron pair donor, and accept this H+ as a base does. So let's have a look. Which is the strongest correct order of pH values of these solutions? So I'm looking at answer C, because ethylamine is the strongest base that would have the highest pH value, and then next would be ammonia, and then next would be phenylamine. So strongest base, medium strength base, weakest base. So we're looking at answer C.